Tell me when to start. Hi from Arlington, Massachusetts. I'm unfortunately unable to be there today, so I've recorded this talk for you. I would much rather be there in person so I could dynamically respond to you, but I will try to be online after my talk is presented to answer questions that you may have. Anyway, let's get into this. So I'll have to share the screen. Okay, and I'm sharing the screen, and I suspect that you can't see it right now, but I will wait until it becomes available. Anyway, I've been programming computers for a very long time. I've been programming them since 1962, I suppose, when I was I suppose I was in high school in Brooklyn, New York. And I, of course, I was a member of the Columbia Science Honors Program, which is a high school student program in which I got to use some computers at Columbia University. When I was starting dealing with computers, this is what computers looked like. Okay, this is not the one at Columbia University; it's the NASA one. But a similar IBM 7090 system or 7094 system was at Columbia, and these machines were ridiculous. Okay, this machine cost multiple millions of dollars, something like $15 million. However, it could address only 32,268 words. That's 2 to the 15th words, each of which had 36 bits. The machine ran at about 2 microseconds per cycle, which is, I suppose, a 500 kilohertz machine. And each instruction word had an address part and a decrement part from which we get the words car and cdr for Lisp. Car being the contents of the address part of the register, and cdr means the contents of the decrement part of the register. MIT had 2 of these machines, by the way, and besides Columbia had 1. But when I got to MIT, I was not using one of those. At Columbia, I didn't use this either. I used an IBM 650 and 1620, which were little machines, quote little, meaning that they were much smaller than this, but they were still humongous objects. Anyway, getting on with this, when I got to MIT as a freshman, this is not a freshman, but when I started looking like this. I looked like this, and computers looked like what you saw. What you're seeing here is a DEC PDP-6 computer, the one that ran MacHack 6, which was a chess program that actually played in tournaments. And here's a little thing saying it played in a tournament. The machine had a telephone on it. This telephone was an MIT extension telephone, and the phone number on that telephone was 6765, which is Fibonacci of 20. So when Bill Gosper answered the phone, he would always say Fibonacci of 20. Anyway, let's see if I get my stuff here. Okay, so for some reason my pages are flipping. This machine costs somewhat less than $1 million. The machine can address 2 to the 18th 36-bit words. That's a little bit more than a megabyte, but that's a lot more than the 7090 could have. And we needed big memories like this to do things like Maxima, the first significant symbolic manipulator. To get this big memory, we contracted to a company called Fabritech that made it. It took them a year to make it. Okay, and it costs, according to Fabritech, something like $240,000, with $380,000 as far as I can tell from MIT's records, and that was in 1967. The memory was called the Moby after the whale Moby Dick, since it was considered an enormous amount of memory available at the time. This was one of the largest computers in the world from the point of view of memory. Well, since then, I've learned a lot about computing. I've designed and built lots of electrical circuits. I've worked in artificial intelligence. I've been involved in the design of some novel computers. I've participated in the invention of computer languages. I've done numerical simulations of celestial mechanics type situations, and I've written large symbolic systems, but I've never given up programming. I love programming because programming is fun. So that's the actual content I want to get into today. So let's start by saying, what is programming? Okay. And programming is certainly not coding. It's not the mechanical transformation of well-defined specifications into executable code. That's the job we make compilers for, okay? One of the most important problems here is there are usually no good specifications to meet. We can't just transform a specification because we don't have any. We have vague understandings of what we want the behavioral system to be, and we know what constraints are on what's feasible to implement. Good specifications almost never come top down from the boss. Okay, we figure out what we can do, and then we write specifications for what we're able to accomplish. And that's what I'm really that's what real programming is more like, as you can see over here. So more like that, programming is more like abstract engineering design. It's a joint exploration of what the achievable specifications are and the possible implementations that are, and they're directed at some partially defined, not fully defined goal. We don't really know what we're trying to do. We're trying to get something that does something in some region that is interesting to us and that has some sort of behaviors we'd like to get. Unlike the design of other physical systems, however, there are no physical limitations. It's not that we have to worry about, for example, do I have a tolerance of 1 millimeter in where I'm going to place this part, or 1,000th of a millimeter? We don't have to worry about the kerf of a cutter. We don't have to worry about tolerances of parameters like that. We have only 1% resistors. Okay, and what we are limited by in the programming is our ability to think. How do we organize ideas? How do we control the complexity of these huge machines that we're building that are virtual machines inside of our computers? After all, the number of parts of some interesting system is way larger than the number of physical parts you could actually put together in any real machine. So I get to choose things when we're programming. We make representations, algorithms, and levels of abstraction. Okay. Now, what does that really mean? What is it like? What does it feel like to be a programmer? Okay, that's a really interesting question. And what I decided to do is ask an expert in programming people. Okay, poets are people who program other people to have emotional reactions of the reactions that they want the person to have. So a famous poet who is very, very good was Edgar Allan Poe, and he actually explained how he wrote the poem "The Raven," which is basically intended to make you feel sad about sort of a lost love, a person who apparently died or something. Okay, and he really don't. He doesn't say it at any point in the poem what he's actually lost. But it's a woman by Lenore, I believe. Anyway, I'm going to read to you an explanation he made of how he wrote The Raven. I select the raven as most generally known. It is my design to render it manifest that at no one point in its composition is referable to either accident or intuition, that the work proceeded step by step to its completion with the precision and rigid consequence of a mathematical problem. Most writers would positively shudder at letting the public take a peep behind the scenes, at the elaborate and vacillating crudities of thought, at the true purposes seized only at the last moment, at the innumerable glimpses of idea that arrive not at the maturity of full view, at the fully matured fancies discarded in despair as unmanageable, at the cautious selections and rejections, at the painful erasures and interpolations, at the wheels and pinions, the tackle for scene shifting, the step ladders and demon traps, the cock's feathers, the red paint and black patches, which constitute the properties of literary histrio. By the way, the word histrio is an old word for actor, so it's literary actor. Anyway, isn't that really what programming feels like? Okay, it isn't more like what you see from what you just heard from Edgar Allan Poe. It's not at all like transforming some specification into a by mechanical means into code. Okay, in any case, it really feels to me more like a creative art. There are creative arts like architecture and music and so on. And for me, for example, I'm somewhat familiar with mathematics and theoretical physics. They're creative arts too. You're trying to invent theorems that are pretty in mathematics. You're trying to invent explanations of the physical world in theoretical physics. Okay, so that's a different kind of thing. Another thing that seemed at the time was, let's get into it and see what this is like. Okay, when I was a freshman at MIT in 1964 to 65, I was shown Lisp, the programming language. But there was this book called Lisp 1.5 Programmer's Manual. And there was also another book by Information International called The Programming Language Lisp. I suppose that was by Daniel Bobrow and Ed Berkeley. And you may have heard of Ed Berkeley. He was the guy who made the GENIACs. But then again, maybe you're not old enough to even think about that. One evening over a Chinese restaurant dinner with other Minsky's hackers, someone, I think it was Gosper, explained the eval apply interpreter to me. This was a revelation that changed the course of my life. Okay? So what you're looking at here is the core of an evaluator for a language-like scheme. It is made out of two parts, eval and apply. And it's written in completely concrete form. You use cars and cutters and things like that. I'm manipulating the data structures directly. It's not abstract syntax like I would have if I wanted to write a modern professional program. If you look in SICP, you will find a beautiful version of this, which is in abstract syntax. And if you look at one that wants to have extensible abstract syntax, you can look at the new one with Chris Hansen that I wrote with Chris Hansen. But in any case, this is a very interesting program. And I spent all night thinking about it after having it explained to me. Okay? It wasn't exactly this program. It was a more primitive version of Lisp, but that doesn't really matter. Okay. The critical thing is, after having thought about it for a very long time, I realized that this is the essence of the matter. There's a process called eval, okay, and there's a process called apply, which are represented by those procedures. And what eval does is takes an expression and an environment which contains the information required to give meanings to the free names, the free variables in the expression. An expression like the sum of A and 3 has got two free names in it, A and the sum plus, okay? And something has to give meanings to those. The environment is a mapping from the names to the meanings, okay? And so it takes that and it transforms it into a procedure and arguments, because by evaluating the operator part of the expression, you get the procedure, and by evaluating the operands part, you get the arguments. Apply then takes the procedure and arguments, binds the arguments to the formal parameters of the procedure to make an environment in which you can evaluate the body of the procedure, and that goes back to eval. Okay, so this is the whole idea, and to me it was very important because it seemed all computer languages had to work this way. In fact, the computer itself has to work this way too, and it does at the implementation of the electronics level too. There's something which is basically doing exactly each of these ideas. Okay, so this is the first revelation I had here, was that, and of course, revelations are often shown in mystical symbols, even though there's no real mysticism. But the feeling here is, wow, that was very important. Okay, well, at the same time, when I was an undergraduate, and in fact, the second term of my freshman year, I was taking freshman physics. In that class, we were learning electricity and magnetism from the perspective of special relativity. A high point in that class was the appearance of Maxwell's equations. Here they are. Maxwell's equations are among the most beautiful expressions of physics. Okay, it talks about fields, E, which is the electric field, and B is the magnetic field. And the electric field has sources, which are charges. So that what you see here is that the charges are the sources of electric field lines. And the magnetic field has no particular sources, because we don't know about magnetic monopoles. We're not sure we have any. But the magnetic field arises by looping around currents. J is electric current, and electric current produces a magnetic field around it. That's what this says. And there's another piece here that says changing a magnetic field produces a rotating electric field as well, like an electric field that has a net curl. Now, at the beginning, when Maxwell first thought about these things, he didn't have this expression here, 1 over c dE by dt. That's called the displacement current. And that was not there, because these were all laws that were determined before Maxwell by people like Ampere and Faraday, okay, and Gauss. But what happened was that also Benjamin Franklin realized that charge is conserved. It's a fluid, it's a material, that the current is balanced, the divergence of the current is the rate of change of the density of charge. Okay, so that It turns out, however, that the Maxwell equations without this term are inconsistent with conservation of charge, and Maxwell realized that, so he stuck in this term. Okay, that seems like a little idea, but the next day, or maybe the same day, he did a little bit of math and came up with what's now you see as the wave equation, the electromagnetic wave equation. This part is basically saying that electric field propagates as a wave with speed c. Okay, this is a wave equation right here, and the C that was determined came from information about how electricity and magnetism worked, which actually were not written as C here, but rather they were written as combinations of the magnetic permeability and the dielectric constants of materials. Okay, so from the basis of knowing that for free space, those numbers, he computed the value of C, and by golly, it turned out to be approximately the same number as was deduced from observing the motions of the Galilean satellites of Jupiter. Boy, so at one step, he discovered that electricity and magnetism were what light is based on. Light is basically electromagnetic wave. I wish something like that would happen to me, that I would have a discovery like that. That would make me really feel good. Okay, but unfortunately, it doesn't happen to everybody. This happens once every few hundred years that anybody has such ideas. But the next thing is that what hit me after seeing this is I learned this from Gosper and studying eval apply, and I learned this from Maxwell equations in my class on E&M, and they're analogous. Okay, that the eval process produces something for apply to work on, apply process is something the eval works on, and the changing magnetic field produces an electric field, changing electric field produces a magnetic field. By golly, we get electromagnetic radiation. Here we get evaluation of expressions, okay? But that's even more, it's more general than that. We always have dual variables in things like physics. So for example, we have things like position and momentum, okay, or energy and time. In the case of position and momentum, it's pretty obvious. Okay, we have a system that depends upon knowing where it is and how it's moving. Okay, if it's in a particular place and it's moving with a particular momentum, then the momentum tells us how to get the next position. The position tells us what the forces are, because the forces depend upon where things are, and that tells us how the momentum has to change. Okay, and that's general about everything. Okay, so we have dual variables and we have duality appearing in computation. Okay, now, of course, that's fun. The fun is that there's philosophical insight. It's sort of, you're thinking about things that are far more general, that are almost cosmic in the way you think about them. Okay, and this turns out to be very common in everyday programming. Everyday programmers always run into deep philosophical issues. So, for example, a good one is, what is the meaning of the word Chicago? What's going on here? We use the word Chicago in programs. We might write it as in part of a database that's telling what sites there are in Chicago to go see. Okay, but the problem is that the city is not in the computer. All that's in the computer is this 7-character name, presumably, and maybe lots of property lists on it and things like that. Okay, the real city is changing all the time. Okay, so it's not clear what that symbol actually refers to. And this is the kind of thing that philosophers worry about. I certainly, when I was an undergraduate or graduate student, had long, horrible fights with a philosopher by the name of Jerry Fodor about what does the word Chicago actually refer to? Not clear. And when you get into things like, what does it mean by identical? Identical is the same kind of thing, okay? Because here's the beautiful example. When I teach classes in this sort of stuff, I take 2 pieces of chalk and hold them in front of me to show the students. They're look identical pieces of chalk. They're brand new pieces of chalk. And I say, how do you know that this is really 2 pieces of chalk, or it's 1 piece of chalk by an illusion, by some sort of using mirrors or something, as a magician might? I'm showing you 2 views of the same piece of chalk. How can you tell? And the answer is that I break one of them and the other one doesn't break. Okay. The critical idea there is data structures are identical if only modifying one modifies the other. Okay, mutation is about change in time, and mutation is essential to the question of identity. The test of identity is that if you change the thing, if you modify it, the other copy that you think of modified as well, the alias. Okay, now pure functional programs have no such mutation. So that's pretty weird. Okay, because I can mostly transform a program into a pure functional form by inventing a store that gets pushed around, over the entire behind the scenes, as you might do with monads in Haskell. Okay, so you can do that, but you can do it all the time, and that means that if you were sort of the deity who built the system, you can see the thing from a transcendental point of view as not necessarily having mutation. It's just this arrangement of pipes around. Okay. On the other hand, if you're part of the system, if you're immanent to the system rather than transcendent around it, then you can, for example, if you're a particular process and you talk to some other process, that other process changes as you talk to it. Of course, that's because it has internal state that it appears to be changing. And so a programmer has to see it from both points of view. This is a very deep philosophical kind of situation. The problem occurs in quotation. We use quotations all the time. We have pieces of code that are quoted when we, for example, do interpretation or compiling or manipulation of algebraic expressions. But the problem is one with substitution. You're all taught in elementary school that you can always substitute equals for equals in an expression, but that's not true if you have a quotation. For example, if I tell you that John knows that the morning star is Venus, and we all know that the evening star is the morning star, that we can't deduce that John knows that the evening star is Venus. Okay, so you can't substitute into a quotation equals for equals. And even in machine learning, we have problems that are philosophical. Okay, what does it mean to be evidence? Okay, there's a claim all ravens are black. Well, every time we see a new black raven, okay, that's evidence that the ravens are black. Okay, but unfortunately, that statement, if something is a raven, it is black, is logically equivalent to if something is not black, it is not a raven. But seeing my white teacup, okay, which is certainly not a raven, does not give me any feeling that there's better evidence that all ravens are black. So this is a problem which has got a name, Hempel's Raven's paradox. And if you look in Wikipedia on it, you'll find all sorts of arguments about things like Bayesian explanations of this. But this is the kind of thing the philosophers worry about. And it's not clear that those answers are right, and they'll be worrying about this for another 100 years. But we have to address these things every day of our lives as programmers. Okay, so I think there's something very different about being a programmer. Okay, now, but we have bugs. Bugs are important. Okay, bugs occur in every program. There's no way to avoid them. I'm not. I don't believe what Mr. Dijkstra tried to teach us, which is that you should always completely prove your program correct before you try to write it. Okay, you should make sure that you have every step exactly right, and you should be ashamed if you have made a bug. No, that's not what I see it like that at all. In fact, bugs are opportunities to learn. It's fun to have bugs, and they're going to be for a reason we have bugs. Debugging with good tools is also a nice adventure. It's fun to do it. Bugs, by the way, should have names like fence post error and read write. They should become friends of ours. We should have a whole community of bugs that we all know of, and every one of us knows those bugs, so that we know that the named bugs have specific mitigation strategies we can apply. I claim that bugs are consequences of a powerful way to design. Okay, a powerful strategy. The reason is because we're finite human beings. We can't think of everything all at once. So we have to plan, and planning requires simplifying to achieve an approximate result. The result of simplification is, in fact, that we haven't thought out everything. So there are bugs. Okay. But what we do is we then debug the system that's sort of in the right direction, that's approximately right, to make one that's more like what we want it to be. Okay. And this is a process which I've given a name to. It's called problem solving by debugging almost right plans this DARP, okay? And I think it's actually very serious. Let me show you about it in a more concrete example, actually a more real physical hard example, okay? Let's give an example from electrical engineering. Now, I'm not going to be teaching you electrical engineering, so don't worry about whether you understand every detail of what I'm talking about right now. But it turns out there's a simpler way to show an example of the strategy than I can do in, say, programming. Supposing we need an electrical filter with a given frequency response. This is the magnitude of response versus the frequency. And supposing you want one that cuts off, that has no response at DC, okay, and has turns around, so it has starts having responses around 30 hertz. It sort of flattens until it's about 3,000 hertz, 3 kilohertz, and then it dies off. This could be one, for example, for a filter for pulling out speech sounds in a noisy environment, because human speech is basically between 30 hertz and 3 kilohertz. The telephone system never passed more than about 3 kilohertz. So what we're trying to build is a mechanism which has inputs and outputs and has a response which is this shape. Okay, that's where the H is called the system function, and it's in terms of something called complex frequency, which we'll talk about. Anyway, this has very no obvious discrete features on it, but I can pick them out, make some discrete features that solve the problem. It goes through 0 at 0, it turns around at 30 hertz, and it turns around at 3 kilohertz. Okay, those correspond to in the complex frequency domain, okay, two what's called poles and a 0. Okay, the 0 at 0, and this pole is at minus 30 hertz, and this pole is at minus 3 kilohertz. Okay, and what that means is that I can synthesize the behavior, the system function of this box I'm trying to make by making something that has, in complex frequency world, this is Fourier transforms, it has a ratio of two polynomials, one of which has got a factor of s in the numerator, and in the denominator there are two factors that go to infinity if I touch these poles. Okay, why that works, I'm not trying to explain that. I'm not teaching you electrical engineering. However, what I have also in my mental library is plans for putting together pieces of machinery so that I can make a more complicated system function from simpler ones. So, for example, if I want to make a sum, well, I can make the inputs in parallel and the outputs in series, and that gives me a sum plan. I can also, for example, have a factorization plan. If I want to make a product of two system functions that are simpler, I can make that by cascading two pieces of electrical circuitry. Okay, these are approximate plans. They're going to have bugs, but in any case, I can also use the fact that I have factors that I can make up. So I'm going to use this factorization plan, this one, because I see I can make something with a pole. Okay, well, why I can make something with one pole, it's not your business right now, and I don't want to teach that, but I can make one by putting together a capacitor and resistor like this. I can make something with a pole and a 0 by putting it together, a capacitor and resistor like this. So I can make the parts of this diagram over here, okay, as a factorization, because what I'm doing here is, here's part of it, Ks over S minus A, and the other one is 1 over S minus B. Okay, so there's my factors. So I put it together and I'm going to try it out, and it doesn't work. Okay, it's a failure. Why is it a failure? Well, there's a reason. The reason is because these computations were done assuming that this is a voltage divider, which means no current comes out of here, and this thing can take an arbitrary current in from a voltage source. And that's true of this one as well. So when I put them together, okay, this guy is sucking current out, but this guy's assuming no current's coming out. Contradiction. Okay, that's a name. A bug like that's got a name. It's called a loading bug. This circuit, this subcircuit is loading this circuit. Okay, loading bugs can sometimes be solved by, for example, putting in an amplifier. An active amplifier, can provide, can measure the voltage from here to here without disturbing it, and put out a voltage which can pump as more arbitrary current into here if that's what I need to do, because there's a power supply inside the amplifier. So this works, okay, as an example of a patch, okay? But the big idea is not that at all. It's the problem solving by debugging almost right plans. What you see here is a simplified example to bring out the essence of the strategy. We have a planning library with lots of plans, of which I showed you two. Each plan gives a way of composing a stab at the solution. Okay? And of course, all problems are recursive, so sub-problems have sub-problems and so on, so you have to have plans for every level. There are named bugs associated with each plan. For example, a factorization plan has in my head a loading bug. The summation plan has something called the ground short bug, which I didn't explain, okay, but it's another one. Iteration plans may have funds post bugs. Concurrency plans may have reader-writer bugs, as you all know about. And there are named patches for each bug in the plan. Loading bugs could be sometimes patched with an amplifier, but an amplifier patch may not do the job in all cases. I might need a passive filter. It's a different thing. So each bug patch may itself have bugs. Okay, so that's sort of explaining what why problem solving by debugging almost like plans is sort of a rather deep issue. Okay, now what I'd like to do is talk about some bugs that are not much fun. Okay, here's some that are not much fun. We call them ugly kludges. Okay, and all programmers know about ugly kludges. And we always they're tedious, they're unpleasant. Okay, they're because somebody didn't think carefully. One example of it, which I always like to complain about, is the language C. Okay, and C++, its descendant, I suppose. They're awful. Okay, they're full of traps for the unwary programmer. Think about the fact that almost all, if you read the reasons why you have to get a new kernel quite often, it's because there's lots of bugs of memory management or something like that. Mostly because the thing was written in C, and that people have to manipulate their memories in ways that are just not clear for humans to do. Okay, but there are more elementary problems like this. Consider Python, a nice language that we use for teaching things, and which quite often everybody uses. Notice that the constructor for a dictionary produces a dictionary, which is denoted by a pair of braces. Okay, the type of a pair of braces looks like it's consistently a dictionary, but if I put something in between the braces, whoops! Now I have something called a set. That's weird. Can I make sets? Well, let's use the set constructor. Well, if I do that, I would have hoped that I would get something like this. But what do I get? I get this. Whoops. Okay. And what happens if I put set, if I take the set of that? Oh, now I've got the identity function set. That's pretty weird. Okay. It just isn't consistent. It doesn't make sense, but it gets worse. Okay. Here's even worse. Here I have a list of two elements. Okay. A list is denoted in Python by square brackets. Okay. Delimited by square brackets. The first element of the list is foo. That makes sense. The rest of the list is bar. There's a list containing bar. That makes sense as well. The first element of a list containing one element is foo. That's fine. The rest of it is the empty list. Okay, that's all fine. I like it. Now, supposing it's tuples. The difference between tuples and lists is notationally they use round brackets, parentheses, rather than square brackets. Okay, but here, the 0th element is foo, as I would expect. Okay, but if I've got a singleton, okay, I get F. Huh? And the rest of it is the OO. What happened? Well, of course, I know the answer is that that tuples are defined in terms of the comma. The comma is what makes something a tuple. And I would have to put a comma here to get what I thought I was going to get. But this is just inconsistent. It's nuts. Okay. And I can't imagine anybody inventing something like this without having smoked something really bad. Okay. So anyway, let's talk about something more fun. Okay. In 1992, I spent a year at Caltech learning about general relativity by hanging out in Kip Thorne's group. That's the people who also did the theoretical part of LIGO, the laser interferometer that was used for discovering gravitational waves. while I was there, I was also thinking about programming what I learned. I always use programs as a way of remembering stuff. It's my memory. My memory is the programs I write. And what I do is I learn something, math or physics or some other, maybe biology, and I write a program to represent that so I can read the program later. It's unambiguous, easy to read, and that way I sort of store my knowledge. It's my standard, it's an expression medium that I use. Anyway, while I was there, a friend of mine who was a floating point chip designer from Hewlett Packard, he designed the HP 3000 floating point units, and we used those in the digital orrery that I built earlier in the 1980s. Dan came by and visited me at Caltech, and we started thinking about derivatives of functions, not the derivatives of expressions. For example, what I mean by derivative function is derivative of the function that cubes. Okay, it produces a new function, which when applied to 2 gives me 12. And that's right, because the derivative of the x cubed is 3x squared. Okay, and that would be when applied to 2, that gives me 3 times 4 is 12. So the derivative of a function is a new function. And what we wanted is a method that was neither a numerical approximation nor a symbolic derivation. It means I didn't want to look inside the function and look at its body. This had to be maintaining the opacity of the function. Okay, so we thought about it for a long time, and we just actually discovered what's now called forward mode automatic differentiation. It had been previously discovered by others, but we were ignorant. But it's still fun to discover things, even if other people discover them first. I'm not interested in priority. I'm interested in having the fun of discovery. But in any case, given such a derivative function derivative, I could write things like this. Newton's method is a way of finding the zeros of a function. The places where the function is 0 when applied to some number, what the number to be applied to. Well, if I compute the derivative of that, then I can use that as a function df. Then I can, if I subtract the guess for the 0 from a guess for the 0, the ratio of the function on that guess and the derivative on that guess, we get a better guess. That's what's called Newton's method. And you all learned this at one point or another. And we can iterate on that until we get a good enough answer. And it works. Okay. So here's I'm finding out that cosine and sine cross over at about 0.785 radians. Okay. Now the insight that Dan and I had was actually very interesting. The insight was that the chain rule was the essence of the matter. Okay, that the chain rule was key to everything I do with derivatives. If you have a derivative of f of g of x, then that's the derivative with respect to the argument of f, where the formal parameter actually is replaced with g of x. Okay, multiplied by the derivative of g at x. Okay, or functionally in a more modern notation, Spivak's wonderful book on calculus on manifolds explains this in detail. We have the derivative of the composition of f and g applied at x is the derivative of f applied at g of x times the derivative of g at x. So at one point, we were sitting around thinking and contemplating this, and we realized that the number system was extended to have differential objects which combine a finite part and an infinitesimal part. Composition would work automatically. What do I mean by that? Well, if in fact I invented things like complex numbers, a number was as a pair, okay, of two things, a finite part and an infinitesimal part, okay, and I made all functions have the property that if they took one of those in, then the function's value would be the first part of the result, and the infinitesimal part would be the derivative of the function times the infinitesimal part of the argument. Okay, if I put that in, then automatically, if I took something like that, which is the output of one of these, and passed it through another function, I get the chain rule works automatically. This is a beautiful insight. Okay, and we had that sort of around maybe 5 p.m. one day. And then we sat there for a while, had a little dinner, and said, because we were using Scheme, I could redefine all primitive arithmetic operators to work with our differential objects. by the way, the differential objects were invented previously by a mathematician called Clifford in the 19th century. He called them dual numbers, but they were pretty much forgotten. Okay. So Dan and I had what was called a hack attack. I bet you've all had hack attacks. A hack attack is when you get so excited about some idea that you can't go to sleep until you've solved the problem. Okay. And it really was like that. So Dan and I stay up all night, and by morning we had my MIT GNU scheme system doing automatic differentiation with both unary and n-ary functions. That's amazing. Of course, this was a preliminary plan with lots of bugs. Hal Abelson helped work out the correct theory for multiple derivatives. We had to use some kind of interesting kind of power series, which I'm not going to explain here. And then Jeff Siskin and Perlmutter and Alexei Radul helped debug the idea for derivatives of higher order functions like this. Here, the derivative of a function that returns a function as a value can also be computed this way. Okay. We had it working even this way, but it wasn't quite right. It would get the right answer in almost every case, but in all the cases we ever tried, but there were sort of subtle bugs that were pointed out by Siskin, Perlmutter, and Radul, and by golly, they wrote very nice papers about this. I highly recommend them. In any case, then further happened is that Chris Hansen, who worked with me, figured out efficient ways to dynamically extend the primitive operators of the scheme. From that mechanism, I built a scheme util system that Jack Wisdom and I have used for teaching and research in classical mechanics. We wrote a book called SICM, Structure Interpretation of Classical Mechanics, and we also wrote a book about differential geometry, functional differential geometry, which captures a lot of what I learned in working with Kip Thorne in general relativity, because general relativity is based on differential geometry. The scheme util system basically generically extends everything. All the arithmetic is extended to almost everything you can imagine. And boy, that was a lot of fun. Okay. And things you could do with that, very simple, but they're also very complex. Here's an example of taking a derivative type operator called a Lie derivative, because there are many kinds of derivative type operators. There are covariant derivatives, there are Lie derivatives, there are exterior derivatives, but you can exponentiate the derivative operator, okay, to basically integrate the motion of something which is described by a Hamiltonian, that's how you describe a physical system. Okay, you start with Lagrangian for the physical system, transform it into Hamiltonian, take the Lie transform of that, advance the initial conditions by dt, and look at the coordinates and look at the first 6 terms of that series, and by golly, you got the right answer. That you don't understand what I just did here doesn't matter. The fact is that this is the kind of thing we can do. Okay, because what's really important is this. When Dan and I came up with the idea that we can make differential objects that when passed through a function automatically implemented the chain rule, that felt good. Okay, it really tasted good. Okay, it was delicious. And when the idea was coupled with the technique of generically extending the primitive operator, the arithmetic operators, I immediately knew there was a fruitful plan for a system. The really big fun was the discovery of the plan and the subsequent multi-year elaboration of the resulting system with Hal and Jack Wisdom. Okay, and in fact, an example, our book, Structure and Interpretation of Classical Mechanics by Jack and I, okay, is exactly directed at making clarity for classical mechanics, which is fairly hard. I'm talking about the advanced stuff, which is Hamiltonians and Lagrangians and Liouville theorems and things like that. I'm going to read to you from the preface. Classical mechanics is deceptively simple. It is surprisingly easy to get the right answer with fallacious reasoning or without real understanding. To address this problem, we use computational techniques to communicate a deeper understanding. Expressing the methods in computer language forces them to be unambiguous and computationally effective. The task of formulating a method as a computer executable program and debugging that program is a powerful exercise in the learning process. Also, once formalized procedurally, the mathematical idea becomes a tool that can be used directly to compute results. So, for example, here's a piece of impressionistic mathematics, imprecise, poorly explained in most books. For example, the realizable paths, the actual path something may take through a dynamical system, that's like something like springs and masses or whatever, or the planets, okay? The realizable path through configuration system space of a dynamical system must satisfy the Lagrange equations. These are basically Newton's equations written in a way which is more general. In traditional notation, the Lagrange equations are written like this. This is vague. It's terrible. You don't even understand, unless you are into the culture, you have no idea what this says. Because first of all, it's not actual good mathematics. It's got bugs. There's a type error. I can't take the derivative of a function of 3 variables. The Lagrangian is a function of time, position, and velocity, okay? And so what am I doing taking a derivative with respect to time there? It's not a partial derivative, it's something else. What's going on is that somehow the path is being substituted into the path, which is a function of time, is being substituted into the Lagrangian after we take the partial derivative. That's what's happening. So the traditional mathematical notation is no good, okay? Here's what it really should look like. It looks ugly as sin, but here it is, okay? It's the derivative with respect to time of the partial derivative of the Lagrangian with respect to one of its formal parameters, where the formal parameters have substituted for them the path at the appropriate time. So this is a function of time only. This is an expression which has time everywhere, and therefore this makes sense to take a derivative with respect to time. And this one is the same thing, except there's no derivative there. So the type error would be putting this derivative here, okay? But it depends upon really understanding what was written here is actually this. Okay, now, once you get that in modern functional notation, Lagrange's equations look like this, which are much simpler. Okay, the derivative with respect to, it's d2, right? That's because I'm a zero-based indexing person. Time is 0, position is 1, and velocity is 2. Okay, so I'm talking about the second formal parameter, okay, of a thing which extends the configuration to the state space, which looks like that, the time, the position, and the velocity. And in scheme, I can write it down just like that, which is the same, there's one-to-one correspondence, okay? So I get a completely unambiguous and executable program, which I can run. I can make a Lagrangian for a harmonic oscillator, 1/2 mv squared minus 1/2 kq square. I can have a harmonic oscillator of mass m and spring constant k. I'm going to see what it does for what is the Lagrange equations for that. That is the Newton's equations, basically, the F equals ma equations. And indeed, what it is that this value is 0, which is the mass times the second derivative of the position plus the spring constant times the position has got to be 0. That is the correct equations. And if I give a purported answer, a cosine omega t plus phi, which is true for a harmonic oscillator, all solutions are like that, where a is the amplitude of the oscillation, omega is the angular frequency, and phi is a phase. Then I get a constraint, which is this has to be 0. But if a is up to me, so I can't be 0, and the cosine is only 0 sometimes, so this has to be 0 all the time, which means that the angular frequency is the square root of k over m, which is correct. It's the spread. It goes up with the spring constant and down with the mass, okay, as a square root. So that's just showing how you can use such a thing. And I'm going to summarize now by saying where the pleasure of programming. Programming provides many intellectual pleasures. Okay, one of them is the pleasure of discovery of analogies, of deep analogies between completely disparate worlds. So the eval-apply interpreter and Maxwell equations got me when I was a freshman at MIT. Okay, this leads into other kinds of philosophical contemplations. Every programmer must encounter every day of his life eternal questions. You don't normally notice them because you're too busy thinking about the details. But actually, these eternal questions are there, and philosophers have been worrying about them for a long time. And we have to actually encounter those and actually make use of possible answers to those questions that might be good enough for our current problem, but don't really answer the problem. Okay, Then there's the problem of we have bugs. And I told you why there are bugs, okay, that they're part of our strategy for problem solving for really smart people. But there's also the fun of going after the bug. There's the incitement of the hunt. Boy, it's more fun. I have never had more fun than going after, say, a good garbage collector bug. Okay, spending all day chasing one where I have to look at what's going on in the middle of the word, the detailed words in a computer memory. And then there's the pleasure of discovery of good ideas. Okay, there's high order functions and extensible generic procedures. An example that simplifies automatic differentiation is an example of the discovery of good ideas. And finally, the ability to use programming to clarify other subjects, like I was doing with classical mechanics or general relativity. Okay, that's fun too. It feels so good once you've got a better answer, a better understanding than you would have if you didn't write a program. So I want to conclude this with a charge to you. Happy hacking. Go after, do there, and write programs that make you feel good. Okay, but there's one more thing. I want you to realize that programming is really fun only if you can share your work with others. So please write and use free Libre software. Unfortunately, today I was required to use Zoom on this to make this recording. I feel really bad about that. I feel dirty. Okay, I want to use only free Libre software. That's software that I can give to you, that you can read, you can change it, and you can give it back to me with changes, and therefore we can learn together. We can cooperate. So I want to do that. Okay. If you want to know what this is about, please look at this URL, GNU.org, philosophyfreesoftware.html, to learn about software and freedom. And please join the Free Software Foundation and donate to the Free Software Foundation, because those are the guys who are pushing free Libre software, including things like GNU Linux. Okay. And that's all I really have to say today. I'm going to stop sharing my screen and be happy to take questions. And I would like the recording to be